following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
In part 1A of this lecture series, we went over the basic structure of the periodic table. Now, before we take a look at isotopes, it's important for us to understand the different information presented for each of the elements of the periodic table. So in this portion, we'll now take a moment and review the information given for each element of the periodic table. That'll help us understand isotopes, and then we'll discuss isotopes a little bit further. Great. Let's begin here by taking a look first at figure 1.25. Now, as we see here, elements on the periodic table, they're going to be separated by the number of protons they contain within their nuclei, the number of protons that they contain within their nuclei. And the number of protons contained within their nuclei is given by the atomic number. It's given by the atomic number, as you see up here. Now, the atomic number is going to be the number that is on top of your elemental symbol. Now, for helium is going to have 2 protons, right? It's going to have 2 protons in its nuclei, in its atoms nuclei, as we see here. Now, for neutral atoms, the atomic number not only gives the number of protons, as we see here, but it also gives the number of electrons as well. Now, how about this quantitative value given below the elemental symbol? Well, that's going to give us our atomic mass in atomic mass units, and the atomic mass is going to be is simply just going to be the average mass of the elements of the atoms of an element. Now, the reason why it's going to be the average mass of the atoms of an element is because not all atoms of the same element have the exact same mass. For example, not all hydrogen atoms or all helium atoms or all carbon atoms are going to have the exact same mass. Now, reason being, if we come over here to figure 1.26, atoms of the same element, right, differ in their atomic mass by the number of neutrons, differ in the number of neutrons that they contain within their nuclei, with the number of neutrons that they contain within their nuclei. Thus, atoms of the same element that have differing atomic masses, meaning different number of neutrons in their nuclei, those are what are known as isotopes. As we see here. Now, if we come back over here to figure 1.25 and we look at the atomic mass, once again, therefore the atomic mass is just going to be the weighted average of the isotopic masses based on their relative natural abundance. Okay. And that's what we see here. And in just a moment, we'll demonstrate how we came across this value for a hydrogen atom of 1.0079. Great. Now that we've had a moment to go over the basics of the information given for each element on the periodic table, right? And we discussed isotopes a little bit. Let's delve a little bit deeper now into isotopes on our next slide. Now let's begin here firstly with a formal definition for isotopes. Isotopes are atoms of the same element which differ in the number of neutrons they contain and therefore have different masses, just as we had demonstrated on the previous slide. Now, if you look here at figure 1.27, let's do a little bit of quick review of everything that we have just taken a look at. Firstly, if our elemental symbol wasn't given to us here, and this for hydrogen, right, for these hydrogen isotopes, how do we know that these are hydrogen isotopes? How do we know these are hydrogen atoms? How would we know that? Well, we would know that these are hydrogen atoms because we just stated that elements are differentiated by the number of protons contained within their nuclei. And we see here there's one proton here. Thus, these are hydrogen atoms that we're working with. And furthermore, how can we differentiate atoms of the same element, or the isotopes of an element? Well, we can do so by the number of neutrons in their nuclei. And here we see no neutrons, here we have 1 neutron, and here we have 2 neutrons in the nuclei as such. And furthermore, the isotopes, they're written as follows. You have your symbol, your elemental symbol on the right side, and then on the left side, as your superscript is your mass number. And what is your mass number? Your mass number is just going to be the number of protons plus your number of neutrons. And we already know that since these are all hydrogen atoms, right, over here, that the protium, as we see here, right, it's going to have, as we see here, it's going to have one proton but no neutrons. Thus, its mass number should be 1, just as we see here. There's one proton, one neutron. The mass number should be 2. And as we see here, there's one proton, 2 neutrons. Thus, the mass number is 3. And in the bottom left, as your subscript, right, you're going to have your as your subscript, you're going to have the atomic number. And the atomic number gives you, as we had stated on the previous slide, right? And if we recall, on the periodic table, your atomic number is actually given on the top. It's actually given on the top, right? And coming back here, the atomic number gives us either the number of protons present, or in a neutral atom, the number of protons or electrons present. And since we know that we have one proton in the nuclei for all hydrogen atoms, right, then our atomic number should remain the same as we see here. It's 1, 1, and 1. Now, common problems dealing with isotopes are going to ask you to find the number of neutrons present. And to find the number of neutrons present is very simple. All you're going to need to do is you just take your mass number, right? And what is your mass number again? It's going to be the number of protons plus your number of neutrons, right? Minus your atomic number, And what is your atomic number? It's going to be the number of protons present. So if we look at our equation here once again, all it's going to be is just protons plus protons minus protons leaves us with neutrons. And that's how you would find the neutrons. Here it's going to be 1 minus 1, there's 0 neutrons present. 2 minus 1, we have 1 neutron present. That's exactly what we see. 3 minus 1 is going to be 2 neutrons, thus it would just be 2 neutrons present as follows. Great. Now let's do a little bit of take a little bit of a deeper look now at our hydrogen isotopes. Firstly, we have protium here, deuterium here, and tritium here. And as we see, for our hydrogen atoms, 99.9% of hydrogen atoms that exist have no neutron, right? Thus, they're going to be protium atoms, as we see here, right? And 0.015 of hydrogen atoms that exist as deuteriums, right? They're going to have 1 neutron present. And there's and the unstable tritium isotope, it only exists in trace amounts. Now, if we were to take the average mass, right, of our isotopes here for hydrogen, right, the average mass of our hydrogen atoms, right, that is where we get that value that comes underneath the elemental symbol. It's just going to be 1.0079. Now, one other point that we should note about isotopes, coming back over here, that the chemical properties for our elements, right, they're almost exclusively dependent on the protons and the electrons present. Thus, the neutrons have very, very little effect on the chemical properties, if that, as you see here. Okay, now let's continue our discussion onto our next slide here. Here, we're being given the periodic table by the number of stable isotopes present for each element. Now, as we had stated for looking at figure 1.28, for hydrogen, we had stated it has 2 stable isotopes, right? And that's what we see here. It's consistent with what we had talked about on the previous slide. Now, just like hydrogen, we see here, so does carbon, and so does helium, and so on, has the same number of stable isotopes.